Hi everybody, Cal here with section 3.4, Subsequences and the Bolzano-Weierstrass theorem. So you're going to need to spend a little bit more time than usual reading this section. It's a very important section, has a lot of pretty important concepts. And I will say, like everything else, the book probably doesn't have enough pictures for this section. So we'll certainly be talking about some of this stuff in class, but let me kind of give you a run through of what's in here. We start on page 78 with the definition of a subsequence of a sequence, and I would definitely make sure you know this definition, play with the examples that are after it, make sure you understand what sorts of things are and are not subsequences of a sequence. There's a note down here, 2/3 of the way down the page, that a tail of a sequence is certainly a type of subsequence, but it is not the only type of subsequence. So again, some pretty important stuff here. Now, Theorem 342 is pretty huge. You want to understand why this is true. So make sure you go through the proof here. And it says that any if you have a convergent sequence, then every subsequence also converges to the same thing. Make sure you understand why that's true. Maybe draw a picture. And I really like the examples in 343. A is pretty cool. B is stupid cool. It is awesome. I really like, these are really clever ways of showing a couple of hard limits easily. So compare these to their original examples. We had to really work for those original examples. But using a little bit of technology, it's not so bad. And I really like the technique that they use here to find what the limits are once we know that the limit exists. Moving on. Theorem 344 gives a few characterizations of having a sequence not converge to a certain x, and in particular is a characterization of what you can say about subsequences. So Theorem 344 part 3 is pretty important. It says that there's a subsequence that does not converge to x. In fact, it doesn't even get close to x. And again, I would read through the proof of this one fairly carefully. Now, we have divergence criterion 345, which is really, really important property. This is two really easy ways to show that a sequence is divergent without working too terribly hard. So take a look at 345, take a look at the examples in 346 that follow it. These are all pretty stock things, things that you should be able to understand on the first reading. All right, we go into, at the bottom of the page, the existence of monotone subsequences. Monotone subsequence theorem is awesome. It's a little bit of a hard proof. I'd like you to try to understand it, and the trick here is going to be drawing a picture of what this whole peak thing means. But you definitely want to know what this theorem says. Any sequence has a monotone subsequence. You don't know whether it goes up, you don't know whether it goes down, but there is a subsequence that is monotone. Okay? And the proof there is pretty important. We'll certainly spend some time on it in class, but see what you can do on your own. And then once we know that theorem, it's very easy to prove the Bolzano-Weierstrass theorem, which was important enough that they named the section after it. The Bolzano-Weierstrass theorem says that if you have a bounded sequence of real numbers, it has a convergent subsequence. Well, why? We know that it has a monotone subsequence by the previous theorem, and we know that any sequence that's monotone and bounded has to be convergent. So that's great. The second proof actually tells you a little bit about what the limit of such a subsequence will be, if I'm not mistaken. And it follows the logic of the nested intervals from section 2.5. So let's see. We have a little note under the proof of 348, and it's talking about subsequences of subsequences, which is, interesting. And there's a theorem about that. So let's see. Let x be a bounded sequence of real numbers. Let little x and r have the property that every convergent subsequence of x converges to x. Then the entire sequence converges to x. So it says if all subsequences of a sequence converge to the same place, then the sequence converges there as well. Pretty important. I'm not going to say that this is easy to use by any means, but the negation is certainly easy to use. So think about that. Then we get into a discussion of what's called limit superior and limit inferior, or lim sup and lim inf. This is a concept that people tend to have a little bit of trouble with, but it's not a hard one. The idea is we think about the set of all subsequential limits of a given bounded sequence, and we look at the sup and the inf of that set. So you want to think about, for instance, what happens to the sign of n. It's going to keep oscillating between -1 and 1. And so you can certainly have subsequences that converge to anything you like between -1 and 1. You want to think about what the sup and the inf of that set of subsequential limits is. So the book goes ahead and gives formal definitions. And I think these formal definitions are a little bit hard to work with. I would say that you can use theorem 3, 4, 11, in particular characterization D, and maybe take that as your definition of lim sup, and take the corresponding thing as the definition of lim inf. In fact, it's a really good exercise to state the mirror of theorem 3, 4, 11 for lim infs, and to prove it as well. In fact, that's likely enough to turn up in your homework. And then theorem 3, 4, 12 kind of solidifies a lot of this discussion. It's an important theorem. They leave the proof as an exercise, and I would recommend trying to prove it as an exercise. That's all for this section. It's a tough one, but it's an important one, so you do want to spend a lot of time on it. Talk to you later.